All right, starting the recording then. Starting the screen share, even better, so the Zoomers can stay with us. So welcome back, folks. Happy Garbage Day. Our second to last garbage day of the semester. So I saw that most of you have turned in your homework 5s. Thank you very much. I will be working my way through those and will let folks know when your feedback is available. The reason that I asked you to name the files in a particular way is so that I could create custom links within the homework system so that you can download your files from there. So as soon as I get through at least all the ones that were submitted on time, then I will let folks know when those are available for your feedback. And if you look at your score and you're like, yeah, I got stuff to do, I don't need the extra 1.5 points or whatever you took off, and you're happy with your grade, fine, you're done. You don't have to revise it. If you would like to earn some more points, if things didn't go well or you didn't get a chance to finish everything, then you can revise it and turn it in by the end of finals week for as many points back as your work allows. Let's see, other things to be working on. This week you have a formative assessment whose content we're going to be going over Tuesday and Thursday of this week. So by the end of Thursday, you should be able to answer all the questions. And then you have one last assignment that is not quite ready yet, but I will let you know when it is. It is going to be a path model. And you can use R-Levon, Stata's SEM package, or M+ to complete your last homework. I have not verified that it is accurate using SAS, however. So if you've been using SAS up to this point, you're going to have to pick up something new. You should all have access within the remote desktop, virtual desktop thing through the university to M+ if you want to learn that. I like using M+ for advanced analyses. I use it primarily in the structural equation models class for factor analysis, structural equation models, and IRT, item response theory models. I also use it in advanced longitudinal. So M+ would be a good time to learn that if you haven't had a chance to play with it yet. It's very straightforward in terms of its language. It's a lot easier, I think, than fighting with R. So from that perspective, it's useful. But if you know that you're going to continue working on path models and things like that within, R within Stata, it's fine if you want to stay within those packages as well. So we'll let you know when that is available, and that will be due at the end of finals week as well. So we're wrapping it up. We're on the downhill, like home stretch, downhill slide. What's the metaphor we want to use for this? Those work? Any others? All right, we'll make it work then. Any questions or things I'm forgetting? All right, then we get to talk about some new stuff today. It's actually not new, it's just a new way of approaching it. So the last unit that we're doing here is multivariate models via path analysis, which is basically regression models that are operating simultaneously for different outcomes at the same time, where things can be both predictors and outcomes. I'm going to focus at first for all of this week on path models in the context of what would be a general linear model, so conditionally normal, no link functions. Let's just get that working first before we see a couple examples of what it would look like to do generalized versions of these. One thing that is nice about Stata's options, so Stata has SEM and GSEM and M+, is that they have a bunch of link functions and conditional distributions built into that. R's Levon package, not so much. So you can use Levon to do path models that have binary or ordinal outcomes, but only under a certain type of estimation, what's known as limited information, and it doesn't have things like counts or gammas or any of that other stuff. So there's differences across packages and what the capabilities are with respect to generalized, which is another reason to sort of start with something that is a little bit more straightforward. And in a lot of other places, I would say in most other places, path analysis is taught within the structural equation modeling course. And I deliberately, when I first started teaching SEM in 2007 or whenever my first class was for that, I deliberately decided not to do that. Because you don't need to understand latent variable measurement models to be able to do path analysis. This is just regression. So to me, it doesn't belong in that class. And so when I do structural equation modeling, I assume that you've already had some content in path analysis, and I focus really just on the latent variable measurement side. So that makes it a little bit different. So in terms of what you can and can't do in a path model, you may see things like older textbooks have chapters on path analysis or even standalone books where they make statements like everything must be multivariately normally distributed. Older books say that because older software insisted that must be true. So most of the treatments of path analysis that you'll see in textbooks, tutorials, and used in practice focus on the general linear model case, just multivariate, multiple outcomes at the same time. So the way that I would approach that is thinking of it as a special case of the generalized family models where we have an identity link, meaning we don't worry about the predictions going out of bounds. We assume that the outcomes are conditionally multivariate normal, so the residuals that are left, which we can't always tell until we fit the model. And that means that all of the outcomes would have estimated residual variances, and that means we can potentially have correlations between them to allow the residuals of outcomes to be related to each other beyond just being predicted by other stuff. So this general case is widely available. You can do this in SAS through a procedure known as CALIS. I don't remember what it stands for, but that's the acronym. Stata has two, SEM and GSEM, where G stands for generalized and also multi-level stuff shows up in GSEM. M+ has options to do basically anything under the sun, and it's continually being updated. It's expensive, which is why we have access to it through the virtual desktop. Student licenses for M+ are between $200 and $400, and real licenses go up to, I think, $1,000. So it's a very expensive package. Relative to free, for instance, our Lavaan can do path models, and if you're sticking with the general linear model case, it does just as good as M+, and the results and the output look very much similar. Some older software that you may hear about, Lizral was the very first package that would do path analysis and eventually structural equation modeling in the late 70s, I think was when it was made. And at the time, everything had to be specified in terms of matrices as input. And one of my instructors in graduate school said that, like, in the 80s, when people first started learning how to use this software, if you could run Lizral, you were called a Lizralite. Like, it was like a tribe of people who had conquered the matrices to be able to do this. But that's not the case anymore. Like, there's so many options and there's so many user-friendly options that it's much more accessible to be able to fit these sorts of models. When I learned path models in graduate school, I learned on a software package called EQS, which I don't even know if it's a thing anymore. And AMOS is also a subset of the SPSS engine that does these things. And I haven't used AMOS since probably 2004 or 5 or something, and so I don't know what it does, but that's another thing. So lots of different ways to estimate these models. One thing that they have in common, though, is that none of them use denominator degrees of freedom in their hypothesis tests. So just as we saw for most of the generalized models, you get an estimate divided by a standard error. That thing is treated as a z-test statistic, and then you get your p-value from the z-distribution. So there's no degrees of freedom for that. That means that these models are less than ideal for smaller samples in which denominator degrees of freedom make a bigger difference in terms of what the cutoff would be for significance. Related to that, these models don't have what is known as REML estimation, which corresponds to least squares. They only have a regular flavor maximum likelihood, which is also not as useful for smaller samples. So you will see examples of multivariate general linear models via path analysis in the second part of example 5, which I hope to get to this week for sure, if not today. And then I have posted a new example, 6A, which is multiple group mediation model based on a publication that I helped with for a colleague at the University of Nebraska. So if you want to do path models that involve generalized outcomes, so if you want to predict a count or you want to predict a nominal variable, that's trickier. Stata's GSEM, M+, and then I said Lavaan and R only does binary or ordinal. I have an example on this where I have two binary predictors at the end of a path model that I will at least give you, if not have time to go over, but I'll probably make a video if I don't. And then Vladimir, I think, is working on something with nominal. That is a work in progress. We'll see if we can get that running correctly. We can get it running, we're just not quite sure about the indirect effects. So a lot of the newer focus on mediation is incorporating generalized models. That's a newer line of research and procedures that people are learning. So one big difference between when we switch from the general case to the generalized lies in how you are allowed to let things relate to each other. So this corresponds to the distinction of like a direct residual relationship versus an indirect that we talked about last week or the week before. If you have outcomes that are being treated as conditionally normal, that means they have an estimated residual variance. You can just say, hey, let the residual of this outcome be correlated with the residual of that one. Done. No problem. If you have, say, a count outcome, that doesn't have a residual variance. If you have an ordinal outcome, that doesn't have a residual variance. So then there's no direct way, under maximum likelihood at least, to say that the residuals are correlated because you don't have access to them in the same way. So what you have to do instead is actually incorporate a random intercept as a latent variable. So my very last example will show you how to do that. Something that I didn't know when I initially did the analysis the first time around. So estimation, there's a lot of stuff in here, by the way, that is like for your reference, not necessarily something that I like need you to memorize or that I plan to put a lot of attention to. Because when I first started teaching path models and trying to learn what all the different packages did, when I figured out something, I put it in a slide so I would know for the next time because I didn't trust my memory. So some of this stuff is not going to be relevant to you, but again, I just put it in there so that you have these resources. So path analysis varies in terms of choices for estimation, and this is a distinction that we have pretty much ignored up to this point in the semester because we haven't needed to worry about it. So what we've been doing is known as full information maximum likelihood. That means that you're using the original data to estimate the model, so each individual sets of responses, as opposed to limited information, which means that you're using a summary of responses. So for instance, let me see here. Let me open up something real quick to demonstrate what I'm talking about. Example 6a. We're not going to go over this today, but I wanted to show you a picture. So like this is a prototypical path model picture, and I'll talk about what these conventions mean in terms of the diagram. One of the things in the paper that goes with this that we published is a correlation matrix between all of the variables that were a part of the analysis, where the upper part of the diagonal was one group and the lower part of the triangle here it was a different group. And we also have another table of means and variances. Well, guess what? Even if you didn't have the original data, if you have a correlation matrix along with the means and variances or standard deviations in the variables, you can do an analysis. You don't need the original data. So that's what's known as limited information, because the analysis operates on a summary of the data first, and that's what goes into the estimation process. All right. So if you have missing data, you want the first one, full information, because that way it understands what's not there, and the assumption that you're making is more reasonable about the reasons for the missingness. Limited information then involves list-wise deletion. Another distinction that you will see is a flavor of maximum likelihood that has the label robust, which means that it is adjusting for violations of multivariate normality. And the place I would direct you to read more about this is one of the book chapters on your reading list, Craig Ender's Missing Data book, chapter 5, as the best description of this that I've seen. And my very limited understanding of it is that it relates to derivatives of the likelihood function. And there's some rule in which something about the first derivatives and something about the second derivatives form a ratio of 1. And to the extent that you have excessive kurtosis, that ratio deviates from 1. And it uses the extent to which it deviates to correct other stuff in the model. That's my 5,000-foot view. Read the details in the chapter. I think he's actually giving a talk on missing data today that's free as I speak. I registered for it. It's on the APA website. It's the same series that I participated in early this semester. So that's where I would direct you if you have questions about that. So I'm going to use robust maximum likelihood in path models pretty much as a default, because even if everything is perfectly normal, then it just simplifies to regular maximum likelihood and there's no downside to it. So this is something that's available within M+ specifically. You can correct standard errors for robustness in Stata, but it doesn't correct the fit statistics of the model. So maximum likelihood estimation gets more words attached to it based on all of these nuances. What kind of data is it operating on, and does it allow for deviations of multivariate normality? Notably, though, this is not a link function. Like if you have an outcome that's not normal because it's a count, because it's bounded, or if you have something that's a proportion that's bounded like above and below, robust maximum likelihood isn't going to keep your outcomes from going out of bounds. It's just a way to protect your standard errors. So you may need to reconsider your model if things are very not normal. There is a different version of the likelihood ratio test when you use MLR, though, and I wanted you to be aware of that. So rather than just taking the straight difference, we have to also compute an intermediate value that's known as a difference scaling correction. That uses these scaling factors that show up representing how far off from multivariate normal the analysis variables are. And so then you end up with a rescaled chi-square and then degrees of freedom like usual. And in R, if you use the ANOVA function after you request robust maximum likelihood, it will do this for you. It gets it right. I built a spreadsheet that does this for you. So if you ever need to do multiple or model comparisons and you're using this robust, you can use that spreadsheet as well. I'm not sure about other packages or things, but generally speaking, if you're using scaling factors in the analysis, they need to show up in this test. So just as an FYI for that. This is something that we see a lot more in structural equation modeling and factor analysis, by the way. Okay, so a little bit of preamble there. Now here's welcome to path models. So the nice part about path models is that most of the time, when you read about like an analysis that uses one, it's a picture and not a set of equations. Like the world has agreed on how to make these pictures, and everyone uses the same conventions. It's beautiful. I don't know how it happens, but it's like the one time that everyone agrees to talk about things in the same way. So in these path model type diagrams here, there's only a few things that you need to know. Anything in a box is an observed variable in your data set. And the structure of the data here is what's known as wide data, where it's one variable per column, the way that it typically would be stored. If you had multiple conditions or occasions, those would be stored in separate boxes as well. So anything that's in a box is real. Anything that's in a circle is not real. You can either call it unobserved or latent or leftover. So for instance, in this picture right here, y1 is an outcome. And if you see the arrow going from the x1 box to y1, that arrow represents a fixed slope. So then E is what's left of y1 after it has been predicted by x1 and x2. So E is latent in the sense that we don't know what the residual would be for each person until after we fit the model. The model has to figure out how much residual variance is left over, and that's a parameter. So residual variances are sometimes shown in circles. We'll see other examples of circles for latent variables when you get to measurement models someday in SEM. We'll also see circles as random intercepts because those are also things the model has to figure out. So one-headed arrows are slopes. They go from the predictor to the outcome. Two-headed arrows, like the blue one here, is a covariance. So this is just saying y1 and y2 get to be related, and more specifically, it's the leftover part of y1 and the leftover part of y2 that get to be related. So after you control for the influence of x1 and x2 on both of these things, then they still have something in common, which makes sense because they're from the same person. So like a covariance is like, oh, I don't know why they're related, they just are. Whereas a directed arrow is more like, no, this is my predictor and this is my outcome in the way that I'm thinking about it. And I have color-coded these to match fixed effects versus parameters in the model for the variance. And here are the equations that would go with this picture. Now this part people do differently. So because I'm predicting more than one outcome at the same time, like I can't just have one beta 0. Because the intercept for y1 needs to be a different number than the intercept for y2. So my way of notating that is to put a superscript as to what the fixed effect is referring to. So it's beta 0 for y1 versus beta 0 for y2. Now that gets confusing sometimes because then it sometimes looks like you're squaring something or exponentiating something. If you have like superscripts that are numbers, it gets ambiguous. And that's why I stuck the variable in front of it to be like, no, this is a label. This is not a mathematical operation. So beta for the x1 predictor, predicting y1, corresponds to this path right here. And then beta for x2, predicting y1, corresponds to this diagonal path right here. And then the same thing happens for y2. x1 and x2 do not have a covariance in this model. That's a distinction we'll talk a lot about next, because these are predictors. So like if you run a regression model, you load up your predictors and you know that the unique effects that you get for your slopes are the contribution of that predictor above and beyond what it has in common with the other predictors, right? I call that a unique effect, or controlling for, or adjusting for. So they do have a covariance that's relevant in figuring out what their unique effects should be. It's just not a model parameter unless you turn these boxes into outcomes instead of predictors. So this covariance has to be here because y1 is having its variance partitioned into how much is due to x1 and x2 versus how much is left over. And this convention of putting the residual variance in a circle, the residual in a circle and giving it a variance, I should say, and this alternative convention of a curved arrow, PowerPoint does not do curved arrows. So I had to make it sort of boxy looking just because of the limitations of PowerPoint, but these are usually curved arrows. If you see an arrow of a box going into itself, that is just the idea that that variable has an estimated variance as one of the model parameters. So that will be true whenever you have an outcome. It has that's in a general linear model, has an estimated variance. The R matrix, we talked about this last week in the context of tricking univariate software to do these models. The idea that y1 gets to have whatever variance left over at once, and so does y2, and their residuals get to be correlated, that corresponds to the idea of an unstructured R matrix. So we're not putting any constraints on what these can be, we just let them be whatever they want. That's usually a reasonable thing in the context of path models. Okay, questions so far? I'm already talking fast enough, so I'm limiting myself to 7 up today.
Say it again, like why, like, so I have like a residual y1 and I have a residual y2, but you said that the y1 is that because it's like latent, but why the y2 is not?
Okay, so the question is, why do these look different? I did that on purpose to show you different ways that people will draw it. So there is no difference. These are just different conventions of describing the idea that y1 is not perfectly predicted, it has some leftover stuff. And some people put the leftover idea explicitly as e is a variable, and it's latent because when we don't know what e is until after we do the analysis. Like the model has to figure it out. That's what makes it latent. And this is the same idea, just without the circle. An arrow going into itself is the idea of an estimated variance for the residuals that remain.
Okay, so basically just two ways to express.
Exactly. Yeah, these are two ways to express the same idea. I just wanted you to have seen them because people don't, like this takes up more space. And so if you have a bunch of variables, like doing this makes your diagram squishier. Yeah, okay. Other questions? Zoomers, anything from this group? All right, moving right along. So this is an example of an analysis that we don't need path models for. This picture, which is the same picture that was on the bottom here, I can do this in a mixed package by stacking my data, putting y1 and y2 into the same column, and then I would have x1 and x2 predict both of them. I would have my dummy codes attached to it to turn the slopes on and off for each one. And the reason that I can do this in univariate software is because y1 and y2 have an undirected relationship that can be captured with an R matrix. But what if, that's the next slide. So why would I want to do this in a single analysis? If I wanted to test differences between the slopes, for instance, so if I wanted to know if x1 had a bigger effect on y1 than it had on y2 or something like that, I have to do this in a simultaneous analysis. Otherwise, there's not really much benefit to doing it simultaneously, and certainly no benefit to doing it in a path model. But this type of setup, under a different name, is called an actor-partner model. So I wanted you to have seen this connection. So if you think of like, this is person 1 in a couple, and this is person 2, the paths that go from my thing to my outcome and from your thing to your outcome are called actor paths because it's like your own stuff. versus my thing to my partner's outcome and my partner's thing to my outcome, those are called partner paths. And there's a whole literature on this that makes it, quite frankly, more complicated than it needs to be. This is the type of setup, though. So if you are doing any kind of dyadic analysis, I would totally do it as a path model. I would not do it as a multi-level model. I'm happy to go into details as to why, if any of you happen to care. But I think I've asked this question like 3 times this semester. Does anybody do dyadic data? And no one has said yes. So you can just trust me on it for now. All right, where I thought I was going is coming up soon, I guess. All right. So one other new layer of complication that is different relative to what we've talked about this semester, but not different to probably how you learned regression in the first place, is the idea of an unstandardized versus a standardized solution. So the analysis that we're going to pay attention to is the unstandardized version, which means just using the variables in their original scales. So we have to know what the units are to know like what this slope means. Like what is a unit of x and what is a unit of y? So if the slope is 3, I have no idea of knowing if that's a lot without considering what 3 is related to with respect to units. And so the goal of the unstandardized solution here is what we're trying to do is recreate the variables means and variances and covariances that are being used as outcomes. And we can compute the total and model implied variance that comes from the fixed effects and then add on the residual variance and we get back to the original variance here. So one of the things that we're going to start to pay attention to is how well the outcome variables means, variances, and covariances are reproduced by this model. In contrast, you will also see a standardized solution. And if you learned, like, I think it's usually called like beta coefficients in regression, like the standardized slopes, like you get a B column and a beta column in your output for stuff. That's the same thing as this. So a standardized solution rescales all of the variables so that they have a mean of 0 and a variance of 1, like a z-score. And then you can interpret the slopes in a correlation metric rather than a regression metric. So like a standardized path of 0.3, I know what that is. I don't need to know how my variables are measured because 0.3 is a correlation in a correlation metric. And in terms of the standardized solution, you get R squares for each variable out of that as well, which is useful, and it means the same thing that it does in regular regression. Not all models will have a standardized solution available. It depends on whether there is a way to standardize it. So if you're doing a binary outcome, yes, you can come up with an R square. An ordinal outcome, yes, you can. Something like a count, not as easily. So there's not always standardized if you're in the generalized modeling world. This is where I thought it was going. This, by the way, is what we call an animation fail. So this box is down here before I'm ready for it. Pro tip, when you're building slides for a conference, do not use animation for this very reason. Make a new slide that doesn't have the thing on it and then change slides and add the thing. If you do it as the next slide, it will always work. Animation is specific to whoever's version of PowerPoint is running when you present your material. I discovered this a hard way when I gave an awards talk and all of my animation for 45 minutes was dreadfully screwed up. That was very uncomfortable. So, don't do this like I just did. This is what I get for adding things to my slide deck at the last minute. So this example model is where we had before. You could do this by tricking univariate software, or you could do this as separate analyses predicting y1 and y2, and there's not much reason to do it otherwise. But what if I change my model so that now I'm thinking of y1 as an intermediate outcome and y2 is the final outcome? So a lot of studies will be phrased this way, particularly if they're longitudinal, like you have your proximate outcome and your distal outcome is the way that it's phrased, where like y1 is something maybe that's closer in time and y2 is more eventual. Well, this is equivalent. These two models are statistically undistinguishable. They will fit the same. They will recreate the same means, variances, and covariances. Because if I have a covariance, that's going to do the same thing as if I have a fixed slope. I'm still allowing some kind of direct pairwise relationship between y1 and y2. It's up to you whether that's a slope that implies one came first, or whether that's a covariance that just says, they're related, I don't care why. The M plus code that you would use, by the way, to illustrate how straightforward it is to fit this whole model is just this little piece right here. The word on, it means make a slope. The way that it works is it's y on x, so it's the outcome on the predictors, and you can stack up as many outcomes on the left side and as many predictors on the right side as you want. The word with means a covariance. So the only difference between the top model and the bottom model that changes from the covariance to the slope is replacing the second word with an on. And the way that I talk about relationships is backwards relative to the code. So like I always think about like this is the effect of the predictor on this outcome. That is incorrect. So the way that I make it make sense in my head is to think about on as an equal sign, like I'm writing an equation. When you write equations, it's always y equals the predictors. The order is the same within the M plus code. Within other packages, you have a little bit more flexibility to make things go left to right or right to left in the syntax, but in M plus you do not. So another layer of description here are some fancy words that people use to describe the role of a variable in the model. Exogenous versus endogenous. I don't use these words. I don't really like them, but other people do, and so I want you to know them. So predictors are known as exogenous variables, and my mnemonic for remembering that is the X part, because in my notation, predictors are always X's and outcomes are always Y's. So this is an exogenous variable. Outcomes are endogenous, and I remember that as there's an arrow going into it, so it's endogenous. So what gets estimated depends on whether a variable is endogenous versus exogenous. I just made up another one. Exogenous. Enogenous, exogenous, exogenous, and endogenous. You tell me which of these is real. Like, seriously. So x1, unequivocally exogenous. x2, same. y1, unequivocally endogenous. y2, same. What's y1 here? It's technically still endogenous because it's being predicted, but like from the perspective of y2, it looks like it would be exogenous. So the predictor outcome label gets to be a bit murky because it depends on which particular regression you're focusing on, what the role of the variable is. So any kind of variable that serves both purposes at the same time, it's a predictor of one thing and an outcome of another, this has to be done as a path model. There's no way to trick univariate software into doing this. What people did before path models were more readily available is to do this in pieces. And so like if you see like the process macro in SPSS to do mediation, it does things in pieces. That's less efficient. I also think it makes things more confusing potentially if you have a complicated model, and I encourage folks to do a simultaneous analysis whenever they can. So what gets estimated for predictors depends on how the software is treating them. And this is a good example of stuff that I put here for your reference, but I don't need you to like memorize this. It's clear for outcomes. It's unclear what an outcome is from the perspective of the estimator. So if I have a variable that's an outcome, it's going to get, usually by default, an intercept. So the predicted outcome for it when all the predictors are 0. And a residual variance if I'm in general linear model land. And software usually throws in residual covariances by default for outcomes. But what's an outcome is the question. So in M+, and in the most recent version of Lavaan, truly exogenous predictors cannot have missing data. So if I'm looking at, say, the picture here, x1 and x2 are clearly predictors. If I leave them as such, they cannot have any missing data, the same as what you would see in a standard regression model. Some of you probably discovered this the hard way, right? When you were looking at your homework data for homework 5, any row that doesn't have everything that's in your model is gone. There's nothing you can do about it. Path modeling does not change that. So if you have a predictor that is truly being treated as a predictor, you cannot have missing data for it. It will just kick that whole row out. Doing so, listwise deletion, as it is otherwise known, means that you are assuming about the missing data that it's completely at random, which means exactly what it sounds like. There's literally no reason why that person would not have that value. Your conclusions would not change other than having maybe more power. There's no bias, no problems there with kicking out the cases of missing data. The reason for this is because truly exogenous predictors are not part of the likelihood mountain of parameters that your estimator is trying to find simultaneously. What it does is compute a predicted outcome from the predictors. If you don't have all your predictors, you can't make a y hat. So that's the problem. So there's workarounds to this, and this is where the confusion lies, I think, in the terminology and also what happens with respect to missing data. So the good news is that if you have a predictor that's truly a predictor, that's exogenous, there's no distributional assumptions for it. You can have any kind of predictor you want. It doesn't matter what it looks like. It can be binary, it can be nominal, it can be, two-part, what have you. So old textbooks that say everything has to be multivariate normal and it doesn't distinguish predictors from outcomes are not describing this situation accurately. That's how it used to be. And this is the point where someone's like, what? I thought full information maximum likelihood allows missing data. Only on outcomes, not predictors. So then it's like, can I pretend it's an outcome? Can I lie and keep my missing data? The answer is yes, you can. What? Yes, you can. And that's the trick. So there's a workaround. Essentially what you do is ask the software to estimate an empty model for your predictor. You ask it to figure out what its mean is and what its variance is. Then M+ or Lavon's like, oh, okay, this is an outcome in my model. Now you can have missing data on it. But that comes at a cost of making distributional assumptions, because now it's an outcome. So it has to be whatever the package is telling it that it is. MVN, by the way, is multivariate normal. That's the most common default. So if you don't say anything else, that's what you're assuming. And the extent to which you have a lot of missing data, those distributional assumptions are important in terms of trying to recreate what the relationships would be involving that variable that has missingness. So this is a trick that people use to get as a workaround that allows predictors to become outcomes from the perspective of the estimator, even if they're not predicting anything. Even if there's just an empty model predicting it, it's not really an outcome. So I will show you how to do this trick. That would be another reason to move from a univariate regression type model to a path analysis, is to employ this trick so that you don't have to kick out all your cases that have missing predictors. How this works and what the assumptions and defaults are varies by software. So SAS, KLIS, and Stata's SEM do not make a distinction. If you invoke full information maximum likelihood, it forces everything into the likelihood whether you like it or not. So there's at least one or two of my model examples where we don't get the exact same results across packages because of this distinction. So Lavon and M+ allow you the choice as to whether you want to trick a predictor into being an outcome, whereas these packages do not. And here are the ways that you would ask to do things. So here's a little bit more about what happens with respect to Stata in particular. So given all of this ambiguity about what's a predictor, what's an outcome, what's exogenous, what's endogenous, what's in the likelihood, what's not in the likelihood, I have a simpler way of just distinguishing this. If your variable has a mean or variance estimated for it, it is an outcome from the perspective of the estimation. You can think about it still as a predictor in your head, but it's an outcome if you're estimating anything about it. That means that you can have missing data, but the missing data comes with distributional assumptions for it. So whether that would be considered exogenous or endogenous, technically endogenous, but it works like it's exogenous in that case. So I'm not going to use these terms because I don't think they help. I will call it an outcome if it's in the likelihood, and I will call it a predictor if it's not. So that's my way of reconciling all of this confusion. All right. How are we doing so far? Predictors and outcomes, the end. But you can trick your predictors into being outcomes, which is useful. And that's what people mean when they say, I used full information maximum likelihood to address my missing data. I tricked my predictors into being outcomes so that I could have missing data, is what they should say. All right, so here's another thing that we have not talked about at all, for good reason, because it hasn't been relevant. Model identification and assessing absolute model fit. So we've used the word fit, right? We've talked about distribution fit, like whether a Poisson is good enough or whether we need like a negative binomial stretchy, or whether binomial is good enough or whether we need like a beta binomial stretchy, stuff like that. We've talked about relative model fit. So if I add 3 predictors to my model and I do a likelihood ratio test, did those predictors make my data taller? What we have not talked about is absolute fit in the context of path analysis. Every model that you estimate that has only one outcome in it fits perfectly by definition, because that outcome has an intercept or a set of thresholds, and it has whatever variance parameter goes with its distribution. We don't have to worry about that. The fit distinction is relevant when we have multiple outcomes at the same time, and we have the potential to be wrong with respect to how they relate to each other. So model identification is something that some folks pay a lot more attention to than me. It's not really a thing in path models. It's more of a thing in latent variable measurement models, because those involve latent factors that are imaginary and you have to give them scales. So identifying a latent factor is a separate consideration. The model will generally be identified in path models unless you do something crazy. I'll give you a couple examples of that in just a bit. But what we do need to start paying attention to is the number of possible things we have in our analysis and things remaining, where thing, it means parameter. So if I have, for instance, 4 outcomes in my analysis, here is a formula that computes the number of possible parameters that I can get back. It's the number of variables times number of variables plus 1 divided by 2. That part right there is the number of variances and covariances among your outcomes. The plus v adds back the number of means. So that means if I have 4 outcomes, there are 14 pieces of information that I can use to estimate this model. I've got 4 means, got 4 variances, I got 6 covariances. Then the question is, how many do I want to spend? Do I want to spend them all, or do I want to leave some on the table? So that is where model degrees of freedom comes from, is the idea of how many things could we have added still. So it's data input in terms of number of possible parameters minus what you estimated. So model degrees of freedom is the idea of leftover. And number left over needs to be 0 or positive, otherwise it's not going to work. There are words that go with that. So in terms of what goes in and what comes out, there is a very direct mapping that will help you, I think, understand where degrees of freedom come from. Every variable that is conditionally normal, that's what we're talking about here, has a mean and it has a variance. Those 2 properties of each variable get recreated as an intercept and a residual variance. So the difference is conditionality. A mean is unconditional. Like if I estimate an empty model with no predictors, like beta 0 is just the mean of that variable. An intercept is the expected mean when all my predictors are 0 specifically. But as long as I have an estimated intercept that can be whatever it wants, I will get back to the right answer for what the overall mean is. Likewise, for anything that's being predicted, I have an estimated residual variance for how much of its variability is unpredicted or left over. And as long as that number can be whatever it wants, I will get back to the total variance in the variable, because the fixed slopes multiplying the other predictors are added to the residual are going to get me back here. So there's a 1-to-1 correspondence where the mean is going to be perfectly okay, the variance is going to be perfectly okay, so long as these 2 things are in the model for it. What the output is called depends on whether something is being predicted. So for instance, in M+, they make a distinction of mean versus intercept, which means unpredicted versus predicted, and variance versus residual variance, which also means unpredicted versus predicted. So these properties are generally okay. These are things that you generally don't need to worry about. In terms of misfit, being wrong, these are fine. Here's where we have the potential to be wrong. Every pair of outcomes in the data has a covariance that describes the linear association between those 2 outcomes, and that can be recreated as either a regression path, So the word path means slope. So a directed arrow, path, fixed slope, all mean the same thing. Or I can make it undirected and just have a residual covariance. The same is true of a covariance with any predictor and outcome. If the predictor is not in the likelihood, I can have a path from the predictor to the outcome or a residual covariance, which would bring it into the likelihood. So this is where we have the chance to be wrong. If you don't specify something between every pair of outcomes, you have the chance to be wrong. It's an empirical question whether the rest of the model adequately recreates a correlation between two things if you don't directly allow it to be there. So this is where model misfit comes from, is direct connections between two variables that you've overlooked. And you can either choose to put them all in and cover your bases so that you know that it's not going to be badly fitting, or you can take your chances and leave some out to make a theoretical statement about that. So there's three scenarios then. There's words that go with these scenarios: under-identified, just-identified, and over-identified. Under-identified means broken. It means you are trying to do too much. Do I have a picture for this? Yes, I do. Next slide has a picture of these. Just-identified means you spent everything, you're broke. But it's actually a good thing in path models because it means you can't be wrong. You spent as many degrees of freedom as you had. Over-identified means that you left something on the table. And I had a student come up with a mnemonic for this. Over-identified means you've overlooked at least one relationship. So there's stuff that you could still be added. This is a more parsimonious description of the variable. And this is where we have the chance to test whether the model actually fits if you leave things out. If you leave them out, you're assuming that it's zero. So mapping these words onto some pictures then, let's say that I have a path model that looks like this. I think x1 predicts y1 and y1 predicts y2. This picture right here is over-identified because there's nothing directly between x1 and y2. What you are saying is that x1 and y2 are related, but the way that they're related is by literally multiplying this slope connecting x1 and y1 with the slope connecting y1 and y2. So it's an implied relationship. It has the chance to be wrong. That is in contrast to this relationship over here that are phrased as covariances. The properties of how we get across the paths in these models, which we'll talk about in just a minute here, maybe tomorrow, we'll see, or Tuesday, mean that this model does not say that x1 and y2 are related. It only says that x1 is related to y1 and y1 is related to y2, and that's it. So the overall picture is creating a different pattern with respect to what's related to what. Now, what if reviewer 3 comes back and reviewer 3 does not like your theoretical argument one bit, and they're like, nuh-uh, y2 is the causal agent that predicts y1, and y1 predicts x1. What are you going to say? If you want it that way, sure. But on the basis of fit and on the basis of the predicted relationships that these pictures are creating, you cannot distinguish between this possibility and that one. They are statistically, mathematically the same. That usually gives folks pause, because one of the other words that people use to describe path modeling sometimes is causal modeling. No, there's nothing causal about this. Causal comes from your design as a starting point, not your analysis. So the reality is that what you have access to is a correlation matrix among these three variables. And your model is either going to recreate it perfectly or imperfectly with room to spare. But the way that these things relate to each other, these supposedly theoretical statements, are not differentiable mathematically, at least not in this simple case. They might be in more complex models with lots of relationships and lots of variables. But either way, this is over-identified because I do not have a direct relationship between x1 and y2. It's going indirect through these paths. Here's just identified. In this case, I have a direct relationship of some kind between every pair. It's either a fixed slope in the cases over here, or it's a covariance in the case over here, but either way, I'm done. For path models, this is my recommendation. The reason is you cannot be wrong. You are sure that you are representing your data as accurately as possible with respect to the relationships between these variables if there's something between every pair. And making sure that you've adequately recreated the relationships is a necessary prerequisite for interpreting them. So this is the safest strategy. It is the, what's the word I want? It's the wussiest strategy. It's the wimpiest strategy, according to other folks, because you're not like leaving anything out. You're shoving everything in there. I think that's a good strategy for path models. I have a different opinion when it comes to measurement models. So this is just identified. Under-identified, meaning broken, would be something like this. So if I have two outcomes, there is one correlation between them. There is absolutely no way to take that one correlation and come up with two different slopes out of it. There are ways to embed something like this within a larger model of other stuff and have it be over-identified, but this just fundamentally makes no sense. Even if you can, doesn't mean you should. So in path models, it's pretty difficult to get into a situation where you're under-identified, but basically what that would mean is redundancy. You're trying to estimate too many parameters relative to what is logically possible, and it can't be solved. You will find out the hard way that you have accidentally or perhaps purposefully under-identified your model, because you will get a row of estimates with no standard errors, no p-values, or nothing. And you will get an error message somewhere that says model's not identified. Good luck. So generally speaking, if you only get part of the output, that's not good. Not good at all. All right. Wake up. Speaking of not good. All right, so what are these pictures then? How did this work? And for this, I had to borrow. So I stole this diagram and the logic for it from this person's class notes. So, in full disclaimer. I learned a long time ago to not recreate the wheel, and if I find something on the internet that somebody's already done a good job of, I'll just borrow it with attribution, because it's a lot faster than making your own of everything. So this is a more complicated path model, and this is designed to illustrate what is known as Wright's rules of tracing. I think this is Wright, I want to say 1908 or like 1922 or something, like way old stuff. Like, people came up with the theory of this long before they had the machinery to actually estimate these things. So this is illustrating how these fixed slopes and covariances, so directed arrows are the fixed slopes, two-headed arrows are the covariances, are recreating all the relationships between these variables, A, B, C, D, E, and F. So first question, is this model under-identified, just identified, or over-identified? Are there things missing that could be here? I see some missing stuff. Like F is only directly predicted by E. It's not directly predicted by anything else. So it's over-identified, meaning there's stuff missing. Whether that's a problem is an empirical question. Do you see any redundancies? Like two things trying to accomplish the same goal? No, so we should be okay in terms of this model being identified, estimable. So there are three basic rules that allow you to figure out what the model-implied relationship is from your analysis. And before anyone starts to panic and think they have to do algebra, no, this is a piece of output you can request. So you can just ask as an option, hey, what does my model say my correlation matrix should look like? And it will pop out at you. And then you can compare it to the actual one, and that is the basis of model fit. How well your model recreates the patterns that are in your data. And you can test whether that is done adequately, so long as you have overlooked certain paths and you haven't spent all your degrees of freedom. So one rule is no loops. You can't pass through the same variable twice when you are building one type of relationship. In terms of direction, you can't go forward then backwards, and there's only one curved arrow that you can cross at the same time. So, for instance, B to D. The B path right here is the obvious way that these two things are related, but that's not the only way, because the B predictor is correlated with A, and A relates to D. So the sum total of how B and D are related to each other is those two pieces. And so you can think of this in the same way that in regression we talk about unique effects, right? B to D is the unique effect of B after controlling for A, because A also gets to predict D. And to the extent that A and B are related, this A path and this B path are going to be different than if A and B were not related. If A and B were not related, we couldn't get across them. So the sum total of B to D is these two things. Likewise, if I did C to D, that one is GB, so I can go from here over to B and then down, or I can go from C over to A and then down. So even though I don't directly have a CD path in here, I have a relationship predicted between the two because of the other things. So it's like a convoluted way of saying, well, this causes this, and this causes this, and this causes this, and that's why these things are related. Not because it's direct, but because it goes through all these intermediate steps. And let's see, AE, so that's 2. There's nothing direct between A and E, but there's something that's known as indirect. This is a new vocabulary word. So let's add that to the list. A direct path is a slope. An indirect path is the combination of two slopes. So A is related to E. If I literally can take the A slope and multiply it by the D slope, that gives me part of the relationship between A and E. But then I have to figure out how else to get to E over here, 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 and then over here and here. So this gets complicated real quick. And no, you don't need to figure this out yourself. I just want to get you used to the idea that even though there's nothing directly between some of these pairs of variables, there are things that are operating indirectly because of the other relationships in the analysis. So some examples of what you can't do, like to go from A to B. A to B is just F. Like you can't go down and back and over again. So once you go forward, you can't go backwards. C to D, you can't go down here and then backwards again. That breaks that rule. And then A and C are related only by H. They are not related by the two D's. All right. So this is phrased entirely in terms of correlations, just for convenience. If you're trying to get to the unstandardized regression paths, then each of these fixed slopes would carry with it the variance of the predictor variable it was attached to. So that gets to be even trickier as we get complicated models. So if we take something that's a little bit less complicated, this is a different picture than what I started with. I'm assuming that I've cheated and brought x1 and x2 into the likelihood as outcomes so that they can have missing data. And I think they both predict y1, and then y1 predicts y2. So same question to you. Is this model under-identified, just identified, or over-identified?
Over.
Why do you say over? Because you're right.
Because we can go from x1 to y2
Yeah.
and yx2 to y.
Yeah, I'm missing 2 paths. So how many degrees of freedom does my model have? And don't think too hard. 2. Missing 2 things. That's how it works. So if I go through the math, like these are 4 variables. So I have 4 means. Well, as long as I give this guy a mean and this guy a mean and these 2 intercepts, I'm good. I have 4 variances. Well, I'm going to estimate the unconditional variance for x1 and x2 because nothing's predicting it. And then I'm going to estimate the conditional residual variances for these 2, straight match. So where the degrees of freedom come in is that there are 6 possible covariances among my 4 variables, but I've only spent 4 of them. I've phrased them as slopes for 1, 2, 3 of them, and 1 is a covariance, but I've left 2 out. So really where degrees of freedom come in most cases, is the mismatch between the total number of possible covariances and the total number of relationships you put in, either slopes or covariances. So here's the missing data trick for x1 and x2. This is an empty model. Like, functionally speaking, these are not outcomes. Like, but I'm treating them that way for convenience sake so that I can have missing data. So now x1 and x2 are assumed to be multivariate normal because I've brought them into the likelihood. If I wasn't worried about missing data, I wouldn't do this. y1 then has an intercept, and it has a slope from x1, it has a slope from x2, and then it has a leftover, and then y2 has a slope only from y1. So good so far with that? So like, these are the piecewise equations that lead to this picture. And most software, you specify the model into something that looks sort of like this. You write it out like per variable what's happening. So then, in terms of the relationships between the pairs of outcome, 4 of them are going to be perfect and 2 of them are going to be imperfect. So here's one that's going to be perfect. x1 and x2 get to have a covariance between it. This number will recreate whatever's in the data. Done. Perfect match. The covariance between x1 and y1, also perfect because there's a direct link here. And this is what it would be mathematically. x2 and y1, same deal. y1 and y2, same deal. Now the ones that are not doing those yet. Model implied variances then. These are going to be perfect because each y1 and y2 have the leftover to plug in any holes. But this is what it would be. So the total variability in y, according to this model, y1, is being broken up into the part of y1 that's associated with x1. So it is the variance of x1 times this path squared. The part that's associated with x2, so the variance of x2 times this path squared. Now x2 and x1 are related, so we can't forget that. And so we throw in twice the relationship between x1 and x2 as a function of their fixed slopes. It's 2 times the covariance because the way I think of it is that the matrix is symmetric and the same covariance shows up in 2 spots. I have no idea if that's right, but that's how I remember it. So any math people, can you confirm or deny that reasoning? Twice the covariance goes into these formulas. It makes sense to me. And then the leftover part. So let's say that like all of this is off by some amount. The fact that the residual variance gets to be estimated as to whatever will plug the hole will always get you back to the perfect variance of y. Same thing happens with y2, albeit uglier, because y2 is like 2 sets of paths away from the x's. The ones that are going to be imperfect are between x1 and y2. Because there is an implied relationship that goes through the paths that are here, but to the extent that these aren't enough, then that will show up as this x1, y2 relationship being wrong relative to what it should be. So at the end of all of this big process, I don't want to get too bogged down in the details. The end result of this is that your model is painting a picture, like it is making a covariance matrix. And then you have the real one that was in the data, and it's like, how far off are they? How far off are they is model fit. So they have to be reasonably close before you can interpret the slopes, because if your model isn't doing a good enough job recreating all the relationships, the slopes are wrong, and they're not interpretable. So that's why I think the safer strategy would be to put in the x1 to y2 path and the x2 to y2 path. Maybe they're not different than 0. Great. But that means you're covered. You have insurance against misfit. That's the way I look at it. Okay. 307. Hanging in there? So there's a whole industry on ways to figure out if your model fits. There's the right answer that usually gives you an answer you don't like. And so then people have come up with other ways to answer the question that work better. So the right answer is a likelihood ratio test. Because on the one hand, you have what the data say your covariance matrix should look like, and then you have your model. And to the extent that you haven't spent all your parameters, you're missing some. So you can do how tall is the data in the original form covariance matrix, how tall is the data according to my model, and is my model significantly shorter? So you already know how to do that. The problem with that is if you have a lot of people, that test is overpowered. You can have very, very tiny discrepancies in predicted covariances render as significantly worse. And people don't like that. So they've come up with some workarounds in terms of how to judge the fit of your model. And all of these workarounds, known as fit indices, are compared to one of two things. So if we think about this as a continuum of what would be like the dumbest model ever and the best model ever, that's your continuum. Best model ever is known as the saturated model. It is given to you in your output with the label H1. Unstructured is the same idea. So this means let the data do whatever they want. All the means directly estimated, all the variances, all the covariances can't be wrong. That's your answer key. So we can see then how much worse our model is than this one. And you get this likelihood ratio test as part of your output. It's called the chi-square test. It's the same exact premise. So there are some indices that judge your model against the best possible outcome. Then there's the other perspective. So what's the dumbest thing I could do, and am I at least better than that? That's called the null model, or the baseline model, or the independence model. And this one is each outcome gets to have its own mean and its own variance, but all the covariances are 0. So it says you have no relationships, fight me. That's what it means. So then it's like, well, how much better did I do by saying, no, I have some relationships, see? I got my paths in here, versus 0. So which of these is relative to dictates how to interpret your fit indices. Anything that is relative to saturated, you want as small as possible. Like how much worse than perfect am I? Anything that's relative to the worst model, you want as big as possible. I want to be as far away from dumb as I can. So that's global fit. And there are a bunch of statistics then that work on that. Local fit is where we would go next. And then once we have a decently fitting model, then we interpret the results, but we don't do it until then. And then we think about effect size. So effect size and fit are two different things. Global fit and local fit are two different things. And there's a lot of, I think, confusion and ambiguity about this. I know we're about out of time, so let me just foreshadow where I'm going. Let's say I've got my giant covariance matrix, right? I've got my 4 variables, I've got my 6 covariances, and I can see whether my model fits great. But what if it doesn't? What then? Do I take my ball and go home? Probably not. Sorry, NIH, I tested the model that you gave me $3 million to do, and it didn't fit, so sorry, I'm done. NIH is not going to like that answer. So we revise it. And how do we know how to fix it? Comes down to local misfit. So what if you have a kid who comes home with a report card, and the report card is 3.0 on a GPA? You happy with that? That's not bad. My question would be, how did the 3.0 get created? Did you get a B in all your classes? Or did you get 3 A's and an F? 3 A's and an F I would be concerned about. What's the F in? Is it like art or something that matters, like math? I'm not apologizing. I was terrible at art. Like, did you get an F in PE, physical education? Because that's fine with me, right? You don't want to play dodgeball and the instructor failed you, Godspeed. But if it's something that is going to like have implications for your future, like, you know, language and reading and math and science and things that we use every day, then maybe I need to get you a tutor, or maybe we need to solve the problem. So I look at these two as sort of interchanged. It's like, is your model a little bit off everywhere? Or is there like a giant hole that once you plug that hole, it's going to be fine? So to solve global fit, we look for local sources of problems, and we try to fix those. And I'll teach you how to do that next time, not today. And once again, the reason we haven't had to worry about this is because when you're predicting one outcome at a time, that's just identified. There's no question. It's fine. All right. Any questions before we call it the end of garbage day? I already put the cans back inside my garage and everything. So garbage day is over at my house. Zoomers, anything? You've been a quiet group today. Nope. No one wants to talk to me. I won't take it personal. Let me know if you do want to talk to me, such as in office hours tomorrow. I'll be there as usual. Otherwise, I hope to see folks Thursday. Thanks for hanging. Bye, Zoomers.